Bismillahirrahmanirrahim. We have concluded our session in the last day with starting the step-by-step process to design the filter. Mostly we talk about the Butterworth approximation. If you can remember, we have already developed this equation for the nth order filter. So it comes from the very basic first order filter. We start with the very scratch first order filter. We generalize that for the nth order filter. Okay. So, and we have also started the steps with the design procedure for the Butterworth filter in the last class, where we have just started with the determinations of n and omega c, where n is the order of the filter and omega c is the cutoff of the filter. As you can remember that in case of Butterworth filter, the omega c hasn't been given during the problem statement. So we need to find the omega c based on the other informations. So we have done up to this. If you have any question on previous topics, you are most welcome to ask. If not, then we can move forward. Okay. It seems that you don't have any question at this moment. Okay. Now the second one, the first step was to determine the value of n and omega c. The next one is to determination of the poles of the transfer function. So how to determine the poles of the transfer function? So here in the literature and in this book, it has been mentioned that it is found that the poles of the Butterworth polynomial lie on a circle whose radius is omega c. The poles of the second order filter are shown in figure this. Okay, so there is a question how we can get that for the Butterworth polynomials should be lie on the circle where the radius should be omega c. Let me explain the fact. Just a minute. I need to open. Yeah. So the not this one. Let me open the Word file. Just a moment. Okay, we are ready. And then the thing is, we already know about the transfer functions. We have already mentioned in the in the book review. That is, this is the transfer function we have developed earlier. So we can think of for the nth order filter. For the nth order filter, we can write it like this. So which is this is for the nth order filter. So you can remember this, and from there what we can write the value, like if we can propose like this. This is the magnitude for the nth order filter. This is 1 plus omega to the power twice n, and there is a root over, because root over 1 is equals to 1, where we just take the value before we have omega divided by omega c. So we are letting that omega c is equals to 1. Okay, so this is a very plain and simple uh, observation of the magnitude response. Now, if we just take it like this, where S is equals to, what is S? S is equals to j omega. So omega is equals to S divided by j. So putting that value and having this hs magnitude, we can find this is equals to 1 divided by, we are putting divided by 1 plus S divided by j whole to the power twice n root over. Now what we can do, so we are just replacing the value of omega with S. Now if we write the total equation like this, hs multiplied with h minus s, so then we can write it like this: 1 plus s divided by j whole to the power twice n. There is no root over because we are multiplying with minuses. This is called inverse transfer function, which actually give you the same magnitude as the hs. From this, what we can find to get the pole location, what we need to do, we'll make this is equals to 0. So we can write 1 plus s divided by j whole to the power twice n. This should be is equals to 0. That will give us the pole location. From there, we can write s to the power twice n should be equals to minus 1 into j whole to the power twice n. These are just the mathematical concept we are developing just to show how the pole should be lies on the circle, number 1, and how that circle radius should be is equals to omega c. For this example, we take omega c is equals to 1. You should remember this, omega c is equals to 1. Now in the we can also write this minus 1 equals to e to the power j pi 2k minus 1, 2k minus 1, where this k is an integer, and also we can write j is equals to e to the power j pi divided by 2. Definitely you can put any value for k is omega is a constant, k is an integer value. Here pi is a constant, so you can put the value and you can justify yourself. So definitely you can justify those numbers. Now we can write again s to the power twice n is equals to minus 1 is equals to e to the power j pi 2k minus 1. And what is the value of j? By putting those value of j, we can write together. You can put those value of minus 1 and j on the previous equation, and you can find the final equation as j pi 2k minus 1 plus n. So that is the value you'll find ultimately. And now for s, if we think about only s, what is the value of s? S can be written as e to the power j pi divided by twice n, and then afterwards the remaining will be like the same. So this is the final equation. And what we can mention here, this is for S is equals to e to the power j pi divided by twice n. I'm writing the same equation here, plus n minus 1. And as you can find that this actually lies for any value of the k is equals to 1, 2, 3, up to twice n. What does it mean? Here n is actually showing the pole numbers for the first pole, for the second pole, for the third pole, and so on and so forth. Okay, for any pole numbers, we can have this equation to find out the position. As you can find this equation, it shows that it lies on a circle where the amplitude is 1. The general equation can be found that S should be is equals to omega c, because it should be actually replaced by this omega c is equals to 1. Omega c e to the power j pi divided by twice n, 2k plus n minus 1. You need to understand that the k is an integer value like this. If we are searching for the first pole, second pole, third pole, you need to change the value of the k. However, the value of the n will remain constant for a particular system where n is equals to the order of the filter. So order of the filter is known to us. If order of the filter is known to us, k is also known to us. And we already find the value of omega c, so we can find the pole location very easily. So in general, what we can write, this is the equation. This is the general equation we have found, and we can also write it like this: S is equals to cos. This is j. So we have j pi. So you have this pi by twice n, 2k plus n minus 1 plus j sine pi by twice n into twice k plus n minus 1. We have just considered the pole, which gives us the stable output. There are some unstable, so we are taking those valid poles, not the invalid or non-valid pole. So we'll talk about the valid pole and the non-valid pole as well. However, this is the formula. This is the key formula by which you can find the pole locations when the value of n is known and omega c is also known. For our case, we took omega c is equals to 1. So from this understanding, we can prove this statement. So this is the statement we have found. This is the statement. Let me show that statement. Okay, here. It is found that the poles of the Butterworth polynomials lie on the circle. So we have already proven that, and whose radius is omega c. So we have proven these two facts with this example, the mathematical terms. Okay, I hope that is very clear to you now. So this is that circle. What is the radius of this? The radius of this is definitely is equals to omega c. You can take it like 1, and afterward we can scale up. Okay. Now the things are very simple. This side shows the poles. Those are the poles. Let's say these are the poles. They are not a valid pole, and in this side they are the valid pole, because we know that in the S domain, the poles, the left side will show us the stable system, and the right side they shows the unstable system. So we'll never go for the poles in the right side. So for example, if we have n is equals to 2, so how many poles we have? We have basically the number of poles should be 2, n into 2, n into 2. So n is equals to 2, and we are multiplying with that. This is 4. So within this 4, we should have 2 non-valid or not valid pole, and 2 should be a valid pole. So 2 plus 2. So what we are counting, first of all, we'll plot all the poles, and then we'll cancel out the poles we do not need. So how many poles we have for n equals to 2? We have 4 poles. Now how they will be distributed? Of course, we can find that they will be distributed according to the equation we have already developed, that is S is equals to e to the power j pi divided by twice n and twice k plus n minus 1. We can find that, of course, they have the equal division, equal distance from each pole location. So how many poles we have? We have 4 poles. And what is the total angle? That is, of course, 360 degree. So from there, we can find a theta value. So what is the theta value? For this case, the theta is equals to 90 degree. We got the theta is equals to 90 degree. Now, what will be the starting point of the pole in case of n is equals to 2? That means when n is equals to, n is a even number. So when n is equals to even numbers, then the first pole location should start at theta divided by 2, which belongs to 45 degree first. And then what will be the second one? This is the first one. What will be the second one? Second one should be theta divided by 2 plus theta. So this is the second one. That means 45 degree plus 90 degree is equals to 135 degree. And this is the second one. And you can also find this angle from the general equation. Again and again, we are writing this like e to the power j pi divided by twice n, and then twice k plus n minus 1. What I'm meaning that if we talk about the first pole location where k is equals to 1, k is equals to 1. The first pole location means this is the valid first pole location. This is the valid first pole location. Let take n is k is equals to 1. In that case, we have the angle pi divided by twice n. Twice n is equals to 4. 2 into k. K is equals to 1. So 2 plus n is equals to 2 minus 1. I'm just writing 1 together. So you have the thrice pi divided by 4, which is nothing but 135 degree. So this is the key equation by which you can find the angle of the pole. So where it belongs to. You can directly find the first valid pole. What would be the third value? So this one, how you can find that? Of course, this is equals to pi by 2 plus theta, and that belongs to probably 135 plus 90 degrees. So 225 degree of the angle. And after that, you can also proceed to the next. So adding one more theta, 90 degree, you will find that. So this is very simple. So for n is a even number. So the starting theta value, the pole location should be theta by 2. After that, theta by 2 plus theta, theta by 2 plus twice theta, theta by 2 plus thrice theta, and so on. On the other hand, if n is an odd number, let's say n is equals to 3, in that case, how many poles we have? 3 into 2, that means 6. 3 of those are valid and 3 of those are not valid. So what will be the first location, the pole location? That should be always on the x-axis. First of all, it should be on the x-axis. Then what is the division between or the separation between two poles? That is 360 degree divided by 6. So that is 60 degree. So we can find that after 60 degree, from this will be the second one. After 60 degree of that, this will be the third one, and then the fourth one, then the fifth one, and then probably the sixth one. So these are the and this is the these are the and this distance is of course 60 degree, and all the poles distance should be 60 degree, something like that. So how we can find it? Definitely with the same formula, but we need to just careful about this two things: when n is even and n is odd. Okay, so everything has written here, so you can go through this and easily you can find the pole locations. Okay, so this is the second step we have done, how to find the pole location. Determination of the valid poles of the S, that means in the transfer function. As we have already mentioned, that we have two categories of the poles: one is the valid and one is not valid, and how to determine those things we have already discussed on this fact. We have also mentioned that this is the alpha. If you again consider the actual equation, general equation, pi divided twice n twice k plus n minus 1. From there we can write cos, we can take common of this one, pi divided by n, and then common twice k plus n plus minus 1, and then we have only, this is the common equation, we can take only plus for the valid pole, So let me write it in a fresh area so that it could be visible. So cos pi by twice n 2k plus n minus 1 plus j sine pi divided by twice n 2k plus n minus 1. This is actually showing the pole location. Those are the valid pole. Now altogether we have plus and minus. This minus shows the poles, those are not valid. Okay, so in general we can present it like this. However, this alpha is equivalent to the pi by twice n twice k plus n minus 1. That is the value of the alpha. So how we can find the valid pole? We can find the valid pole by choosing only the value of plus. So however, by this equation we can by this trigonometrical plot, you can find the pole locations. What we need to do, we need to find this value. What we need to find this location, where in the previous section we have just tried to find what is the angle. We have just only find the angle. Now we need to find the actual location of those. We will neglect these two. We'll take this and this for n is equals to 2. For this location, how we can find this? This is cos alpha plus j sine alpha. I have made one mistake in the previous section. Okay, so just let me clear it out. So this is for this B1. This belongs to B1, and for the B2, it would be cos alpha minus j sine alpha. This minus doesn't mean the not valid pole. Okay, so I'm sorry for that, because the valid and not valid pole, it depends on this angle alpha. Okay, whenever I took this alpha is equals to 45 degree, then it gives the not valid pole. When I have taken this angle is equals to this, then it will give the not valid pole. However, when I have taken this alpha is equals to what? 135 degree, it will give us the valid pole. give us the valid pole B1. Similarly, whenever I take this alpha is equals to, let's say, 225 degree, and this is 225 degree, then it will give us the valid pole, but I need to put the plus. However, for the both cases, if I want to take the valid poles with the single equation, then I can write cos alpha plus j sine alpha. This is for what? B1, where alpha is equals to 135 degree with the same angle. With the same angle, if I put a minus there, what is the value of alpha? Again, the alpha is equals to 135. We can also find the value of B2, both of the valid poles. But if I took the value alpha is equals to 225 degree, in that case, I need to write the equation cos alpha plus, I should write this is alpha 1, where alpha 1 is equal to, and this is alpha 2, plus j sine alpha 2, where alpha 2 is equals to 225 degrees. So I can understand, I really can very confident about this. You can find the value of the B1 and B2 whenever you can find those, you have this angle. But for the simplicity, if I can find this value 135 with the simple equation cos alpha plus minus j sine alpha, I can find both B1 and B2. Okay, both valid poles, where alpha is equals to, for this case, is 135 degree. Okay, so the next step has been completed for the value of n equals to 2 and omega 1, omega c is equals to 1. Okay, so the example has been given here for a particular cases. As we know that the angles at which we got the poles are at 45 degree, 90 degree, 135 degree. So as we know that at the angle, there might some mistake here. So this is a 45, and then it should be, there should be plus. Okay, so please change it like this. This should be not equals to, this is plus, as this is a plus. So plus 90 is equals to 135 degree. So for 135 degree, you will have this with this plus, and you have B2 with this minus. So you have, this is B1 and B2. Whenever we have B1 and B2 with the value of omega c is equals to 1, now we can change the value of omega c is equals to 1.5. If the omega c is not equals to 1, then we need to multiply it over there, and we can find that. In the book, we have the actual book, the plus hasn't been given there, so I have added that plus there. Okay. Now to find the expression of the transfer function. So what we have found the value of n, we have found the value of omega c, we have found the pole locations B1 and B2. Now we need to find the transfer function. That is our target. To define a filter, we need to find the transfer function. So HS is equals to, we know this from our previous lectures, this one, where, reminder, from there, what is the pole location? The pole location is minus A minus JB, and from this, the pole location is equals to minus A plus JB. Okay. So now we already found these pole locations. So try to understand that this is equals to S. This is equals to S. So what would be the expression? For the first one, the expression should be S plus 1 divided by root 2 minus J1 divided by root 2. For the second one, For the second one, the expression should be s plus 1 divided by root 2 plus j 1 divided by root 2. Okay. So s plus 1 divided by root 2 minus j s divided by j 1 divided by root 2. Another one is s plus 1 divided by root 2 plus j 1 divided by root 2. So this is the first one and this should be the second one. And we have found this, okay. This is the first one and this is the second one in the denominator. And that is of course showing the pole locations of the system. What about the omega c? Up to now, we are taking omega c equals to 1. So that's why this is the final expression of the transfer function where omega c is equals to 1. Now we need to generalize that omega c value. So now put the value of omega c is equals to 1.5. To do that, we have already found the expression here. So from this expression, we can understand that. So first of all, you need to find this expression. Now s plus 1.5 divided by root 2 minus 1.5 divided by root 2. Of course, there will be j. And the second expression should be s plus 1.5 divided by root 2. There should be a plus j 1.5 divided by root 2. Those are the two expressions. And this is the final expression. So try to concentrate on those numbers, the numbers we are putting, and there is after doing all the calculations we have found this is the expression. This is the final expression you can achieve by this. Okay. Of course, there is of course there is a mistake here. It should be like 1.5 whole square, and that will give this value 2.25. Okay, so there is a mistake in the book. So the steps, if we mention again, first with equation, with knowing the values of passband gain, the stop band, the gain in the attenuation, the frequency for which the attenuation must start. Those are the four components we should understand. Okay, let me start an example, particular example. The previous section is for the generalized section, and now this is for the particular example. For the particular example, design a Butterworth low pass filter for the following specification. Passband gain has been given. So if I draw the Butterworth filter like this, this is the passband gain. This number has been given. So H1. The frequency up to which the passband gain must remain more or less steady, that is the frequency. So more or less that will be steady. This is omega 1 is equals to 100 rad per second. The gain in the attenuation band is 0.4. That is gain in the attenuation band. So it would be like this. This is H2 has been given. And the frequency from which the attenuation must start, this is that point, and which belongs to omega 2 is equals to 200 rad per second. So we need this for information: H1, H2, omega 1 and omega 2, by which we need to find the value of omega c, as well as we need to find the value of n first of all. So step number 1, n omega c, then the pole location B's, the valid pole locations. And after finding the valid pole locations, we need to find the transfer function. Okay. So step by step, we can move forward. So knowing this equation, general equation, we can write this where this is H, this is H, you can say H omega or HS is equals to 1 divided by 1 plus omega divided by omega c whole to the power twice n and to the power half. So that is the general equation. So we have two value, omega 1 and omega 2. For two cases, we can write two equations, equation number 1 and equation number 2. From these two equations, by solving these two equations, we understand that we can find two values. Okay, so first of all, we find the value n is equals to 2.244. That is the value we have found. At this moment, omega c is unknown. We have found the value of n. Now, it has been mentioned in the problem that frequency from which the attenuation must start. So the attenuation must start from the value omega is equals to 200 radian per second. So that means if we think about this, this is our 0.4 point, and let's say this is 0.9. This is the point of 200, that is omega 2. So at least from there, the attenuation must start. If that is the case, then we have found that n is equals to 2.22, let's say 2.24 or 224. If we have two opportunities, n could be 2, we can take it. In that case, what happens? It might happen that the attenuation will not start at 200. It might goes beyond that. So in that case, it might looks that it might goes like this. Okay, so it is a more than 200 probably. Okay, another opportunity is like n is equals to 3, because n must be an integer, because that is the order of the filter. In that case, what happens? It might happen that now it will be before this, the attenuation, will start. So in that case, it is less than 200. So which mentioned that at least 200 before that is also okay, must be. So according to the definition, what we have found, the attenuation must start at 200 radian, means it might be start beforehand, not after 200. So that's why it is always the better choice to take the higher rounding off of the value of the order. If we got the fraction like 2.01, it should be taken as 3, because it is the safe side. If you took 2.01 as 2, then you are you might be in a problem, but it definitely depends on the purpose. For a particular case of this example, we'll take n is equals to 3. By choosing the value of n equals to 3, now you can find the value of omega c, and which is like this, 151.7 radian per second. Okay, so this is the first step. Now we need to determine the value of hs, and this is very plain and simple, because n is equals to 3. Now the total number of pole is equals to 6. So 360 divided by 6 is 60 degree is the division from each other. And since this is a odd number, it will start the pole location from there. So we can find 6 poles, and these 3s are not valid, and these are the valid poles. We can declare that. and how we can find those the value, the location of those. This is pretty simple by using the equation with the angle. So 120 and 120 plus minus. Okay, so we can find those three values very easily. Okay, and now whenever we found that, this is very important portion. Now finding the expression for HS. As we know that this is n is equals to 3. So how to find the third order filter? Of course, we can cascade a second order filter with the first order filter. So this expression, we have already derived that this is the expression for the general expression for the second order filter, and this is the general expression for the first order filter. Now we can cascade those things for the first order and the second order filter. Need to be very careful about this. These two poles actually been showing the expression for the second order filter, and this is for the first order filter. But you do not need to care about this. You can just put those three pole points on the denominators. You don't need to care about which one is for the first order and which one is for the second order. But logically, you can express that this -1 means what? S plus 1 is equals to 0, S is equals to -1. So definitely it shows that for omega c is equals to 1, this is for the first order filter. But even you don't need to care about this. But as a senior student, you should understand the fact. So S plus this and S plus this, these are the two poles, and S plus 1, this is the third pole. So combinedly, it should looks like this, pretty clean and simple expression. Now one thing is missing. We let that omega c equals to 1. Now we need to put omega c is equals to 151.7. Now put it there. Where you need to put that, not into this equation directly. You need to done this calculation before. So what you can do, you do not need to show this. Okay, exactly what you can do with this expression. In this expression, you can write the multiplication factor of omega c at the beginning, and you can get whatever the value you have, and finally you can put it in the denominators. No need to show this step. Okay, so this is a redundant things. So whenever you found these values, three values, b1, b2, and b3, we can move to the final expression, and ultimately we are getting this final expression. Okay, we should congratulate ourselves that we can design a Butterworth filter. We have already designed a Butterworth filter with the transfer function. If we have this, we can also design what? The analog circuit as well. In the next step, we'll talk about those analog circuits as well. But this is very important, as we know that for omega c is equals to 1, these expressions are constant for particular order of the filters. So let's say for the first order, the denominator expression is this. For the second order, the denominator expression. The third order, this is the denominator expression. So how we got this third order? This is from the second order, and this is from the first order. Try to think that this is from the second order expression, and you can also find for the fourth order. Of course, try to understand this. Whenever we are talking about this second order expression, how you can find this? In that case, the pole locations, second order means you have 4 poles, so the valid poles are there. After 135 degree and 225 degree, as far I can remember. But whenever it is the third order filter, try to understand this, why they are different. In the third order filter, the pole locations are such like this. This this and this. In that case, this angle, the first angle, this angle is 60 plus 60, 120 degree. However, in case the second order filter, this angle is 135 degree, and that is the difference, because sometimes we can misunderstood that in case of third order filter, this expression should be exactly like this. That is not true, because for each and every filter, of course, the angles are different. Now, what you can do, take your homework as to find out this value for n is equals to 4 and n equals to 5, whether you can find these expressions. You can find this expression. Okay, so you can do it yourself, and maybe it will definitely help you to boost up your confidence. For the fifth order filter, how to find, since this is a odd number, so n is equals to 5, so total number pole is 10, so 360 degree divided by 10 is 36 degree. What will be the starting pole? The starting pole always at this location. If you can start there, then after 36. Okay, so what will be the fact? So this is very simple. Okay, during the lecture, if you have any question, please stop me. Okay, design procedure specified, the h omega is specified in decibel. So in the other case, we have specified the value with a relative number with like 0.9, 0.4, something like this. Now it will be expressed in the decibel. So you need the formula of the log. So please go through this expression. These are the very simple things. In the first step, we need to consider the log expression, and other than that, everything will remain the same. So you don't have any other changes. And one example has been given here, so please go through this example. I like this book as it has given their examples, very details, so that the student can understand each and every part very easily. Okay. And now this is the important part where we can start to design the active analog filter based on our work so far. Our HS, or you can say H omega, for Butterworth filter, we have designed our Butterworth filter. Now what do we need to do? We need to implement that Butterworth filter. So there are some topologies by which you can implement the Butterworth filter. One of those is called the Shalen and Key structure. Why this is very important? Because by using conventional RLC circuit, you can't implement the Butterworth filter. This is one statement. You can write this statement that conventional RLC circuit, you can't implement the Butterworth filter. Now the question is why, and why do we need this Shalen key or these active analog filters to design the Butterworth filter? Those are the two questions. Okay, so we have started with the conventional RLC filter, and we have designed our expression as 1 divided by 1 plus, let's say, omega divided by omega c whole to the power 2n to the power half. Okay, we have find this expression from RLC circuit design. Okay, there's no problem. However, whenever we try to design the Butterworth filter, that will not be applicable for by the RLC conventional filter. Now I'd like to explain the cause behind that. Okay. Let's start with again the scratch. Like we have R and C circuit, and from there I'll go a little bit faster because you know this. From there, we have this expression. We have this expression of the output versus input. That is also the transfer function. And for the second order, of course, we can cascade those things. And if we can elaborate the transfer function at the end, we got this transfer function. Okay, so this is the transfer function for a RLC conventional circuit. Okay, it looks a little bit clumsy, but you can go through this and you'll find it very simple. I'll upload this. So general form of the second order filter, we already know that this is another general form of the second order filter, where this omega 0 is basically omega c. You can express the value of omega 0 is equals to omega c. Those are the cutoff frequency. The Q is the quality factor, and the K is represent the gain. This is quality factor. This is cutoff, and the K is representing the gain. So when K, normally the K is equals to 1 and omega c is equals to 1 and Q is equals to 1, in that case, we can understand the expression would looks like the same as we know previously. In that case, the omega c looks like this for the second order filter. The cutoff frequency of second order filter is different than the first order filter. So you can understand this. This is the cutoff. What is the cutoff point for the first one is definitely differs with the cutoff frequency of the second one. This is one problem. That means whenever you are changing the order of the filter, the cutoff frequency will change with a conventional idea. If the resistors are equal and the capacitors are equal, in that case, what will be the cutoff frequency? Okay, this is the cutoff frequency. Here the cutoff frequency are the same for the first and the second order filter. So whenever we are designing a conventional RC filter, this is the first order filter. In this case, let's say this is a cutoff frequency 1. This is a cutoff frequency 1. Whenever we are putting the second order filter, the combined cutoff frequency might be changed to cutoff frequency 2 if these values R1 and R2, C1 and C2, they are different. But if we put R1 equals to R2 and C1 equals to C2, in that case, the cutoff frequency, the combined cutoff frequency will remain the same. If they are not equal, how the cutoff frequency would changes the position if they are not equal. In that case, this is for the second order, the cutoff frequency. It relates with the first order cutoff frequency to the second order cutoff frequency. So definitely it will be shifted by this value. Similarly, in general, the nth order cutoff frequency will be shifted by this value comparing to the first order cutoff frequency. This is of course a problem. So simply by cascading two first order filter, we can't fix the cutoff frequency. It will be shifted for higher order filter. So the cutoff frequency will be shifted for the higher order filter. However, by Butterworth filter, we can do that. So this is a significant outcome or advantage of the Butterworth filter, the conventional filter to the Butterworth filter. In case of Butterworth filter, if you change the order of the filter, still you can fix the cutoff frequency with your design. In case of R1 and R2 equal and C1 is equals to C2, the transfer function can be written as follows. So we can write the transfer function like this. As we already know, this is the general equation of the transfer function. So based on that, we can put like this. So please keep in your mind, this is the gain factor. So we'll talk about this gain factor later on. At this moment, just think that the gain factor is equals to 1. We'll show it practically with the circuit representation. In this case, the cutoff frequency is equals to this, because as we know, as we started with the value R1 equals to R2 and C1 equals to C2, they are equal. And if you can observe the fact here, the Q is equals to 0.5. We are not still in the Butterworth domain. We are in the conventional circuit. Why we are taking R1 is equals to R2 and C1 equals to C2, just to fix the cutoff frequency, because we don't want to shift the cutoff frequency. And if you want to do this fixing of the cutoff frequency in a particular point, if I want to draw that, so let's say this one, and where is the cutoff? Let's say, for example, this is your cutoff frequency. This is your cutoff point. Now, for the other case, it might have that same order. The cutoff frequency might changes for the second order filter. So that makes a problem. That's why what we have done, we have taken this cutoff frequency fixed by taking R1 equals to R2 and C1 equals to C2. That solves our problem. If that solves our problem, but it makes another problem, that means based on this equation, what should be the value of the Q? So the value of the Q is equals to 0.5. You need to compare this with this, where 1 over RC, that is S square plus 1 over RC is omega C or omega 0. And then we have Q. We have Q, which is equals to, which must be is equals to 0.5 in the denominator. So it is equals to 2 into S into omega C. So this is the two values. So what we have found here. This is the transfer function. This is the transfer function. How we got this transfer function? We got this transfer function with the conventional R and C. This is from the practical output. Practical circuit calculation for R1 is equals to R2 and C1 equals to C2. We got this expression where it shows that this automatically comes at 2. So 2 means it is 1 divided by Q. So what is the value of Q then? Q is equals to 0.5. So we got the Q is equals to 0.5. And the Q is the amount of peaking around the corner frequency. That actually gives you the quality of the filter. So here the Q is the amount of peaking around the corner frequency. Let's give you an example with this diagram. Probably this will be very helpful. For a filter, for different value of Q, so Q is equals to 10, Q is equals to 5, Q is equals to 2, Q is equals to 1, Q is equals to 0.707. This is very important. And Q is equals to 0.5. For Q is equals to 0.5, you can follow this line here. This is the line. So you can find that you're definitely not choosing this one, because at the cutoff frequency, what we can find, this is the line for the cutoff frequency. I would like to write here. Let's say this is the line for the cutoff frequency. At the cutoff frequency, it actually missing some of the amplitude of your signal. Of course, it is not very good for your circuit design. So if Q is equals to 0.5, it is not a good idea. On the other case, if you have Q is equals to 10, very high value, you can see this very high peaking. So you have very high peaking gain. So it means that very close to the cutoff frequency, your gain will be very high. That will give us a distorted output, not the original output. Now, what is our target in case of butterworth filter? As you know that this is a minimally flat or flat filter. We are looking for this kind of flat expression, which only can be possible when Q is equals to 0.707. The researcher actually tried with a different value of the Q, starting from 0 to some value Q is equals to, let's say, 10. And they found that for Q is equals to 0.707, exactly at that point, it looks like a very flat expression. For what? For this filter expression. This is the expression for this one they have found, where K is equals to, let's say, K is equals to 1. And now that is the issue. That is the main issue, that conventional RLC circuit only can produce Q is equals to 0.5 if we want to fix the value omega C at a particular point. They can't change they can improve this quality factor Q is equals to 0.5 to any other value. If you want to change that, it is not possible. It only can be possible by changing what? It only can be possible by changing this gain factor. You want to change that, you need to have a dynamic gain, so you need to change the value of the gain factor. For the butterworth filter, we need Q is more than 0.5, which is 0.707. We have shown that, which is only possible when there should be some positive feedback from the output. So we need active component, because in case of a passive component like RLC, we don't have any positive gain, that means positive feedback. So the active components are needed. So in that case, one such filter topology, there are a number of topology by which you can design the butterworth filter. One of those are is the Shalen-Key filter for the butterworth filters. So the topology looks like this, okay? And you have two capacitors, and you need two capacitors and two resistors. And this can be shown like this, where the gain is 1. At the very beginning, we take gain is equals to 1, just to make it simple. This circuit shows gain is equals to 1 because you don't have any feedback resistor there, okay? So you don't have any feedback or input resistance over to the inverting port, okay? By analyzing this circuit, we can write this equation, and you can also do that yourself. So this is the expression for this. My main target is not to show you the mathematical calculation. My main target is to justify why we need the Shalen-Key topology for understanding or implementing the butterworth filter. So that we know that again this is the transfer function, and we know the general form of the transfer function. You already know this. This is the general form of the transfer function. From there, by comparing this equation to this equation, we can write that this is our omega C. And what should be the value of the Q? Now you can understand this here in this expression. In the denominator, we also have the Q number, and which actually give us the freedom to control the value of the Q by changing even not touching the value of R1, C1, R2, C2, not touching those things, just by changing the value of K, you can change the value of the Q. It is very important because the omega C basically depends on the value of R1, R2, C1, and C2. So you can fix the omega C by choosing a fixed value of R1, R2, C1, and C2 in your circuit. However, if you want to change the value of the Q, you just need to tune the value of the gain. That will actually give us a huge freedom to control the Q factor in case of the Shalenkey topology. That is the main finding of this kind of topology. The gain, K is the gain. By choosing the value of the gain, we can control the Q, the quality factor, or the corner frequency peaking factor. To make it very simple, we can take R1 equals to R2 and C1 equals to C2 is mentioned as C. If you can put all those values in the very complex, it looks very complex, but it's a very simple equation. Then we can write it like this. It looks like very simple now. Okay, where we can find that the cutoff frequency is this. Okay, nice. And we can find the value Q is equals to 1 divided by 3 minus K. Q is equals to 1 divided by 3 minus K. As we already know that we need the Q is equals to 0.707. We can put it, and from there we can find the K should be 1.586, not equals to 1. This is the gain factor. This is not actually the gain. This is the gain factor. Okay, so we are putting K is equals to 1.584. Now, how to introduce that gain? Now we can put some input resistance and feedback resistance to the non-inverting port just to get the gain. And let's say the values of the resistors are R3 and R4. Now the gain is definitely can be represented by this equation, 1 plus feedback resistance over the input resistance, and we can find the value. We can choose the value of R4 and R3 based on our targeting gain factor. We got it like 0.586. So hopefully now we can design this circuit. One thing is these R1, R2, C1, and C3, they are targeting the cutoff frequency omega C and all other factors. All other factors means where the flat range will be there, where the cutoff frequency, so the stop band should start. All the factors should be covered by this R1, R2, C1, and C2. What is the purpose of R3 and R4? This will give us the quantity Q is equals to 0.707, which will give us maximally flat response, which is one of the key factor of the Butterworth filter. So there are two sections of this topology, and we have expressed our topology with the equation related to the K value, and we have already mentioned the K value is this, and from there we can find the relation between the R3 and R4. Now, if we look back to our original book lecture, they have given this topology directly. They haven't given the explanation. Okay, so I have given the explanation, and this is from the circuit point of view. This is the second order, and this is for the first order. Now they have given the expression for the circuit design for the fifth order filter. So this is second order, this is second order, and this is first order. This is very simple things, but very important for your understanding. So how to choose those values, resistor and capacitor values and the gain values. Okay, how you can choose those values practically from the transfer function point of view. It has been mentioned step by step. So we can start it from the next class, inshallah. how to design. That means we have those numbers. What does it mean? And how to find those other numbers. So we'll definitely talk about those things in the next class, inshallah. So at this moment, if you have any question or comments. Okay, it seems that you don't have any question or comments at this moment. So thank you very much for your presence.